Swayam Prabha. Digital India. Educated India.
So welcome back to the lectures on advanced calculus for engineers, and this is module 1 on differential calculus and lecture number 3, and here we will learn about the Taylor's formula for single variable. So the content of today's lecture, we will be talking about the Taylor's polynomial and then see under what condition this Taylor's polynomial goes to Taylor series, and there will be some worked examples. So the Taylor's formula, this is a generalization of the mean value theorem which we have discussed in the previous lecture. So assume that a function f has all derivatives up to n plus 1th order. So now we are generalizing this. So we are talking about that a function has derivatives up to n plus 1th order in some interval containing a point x naught. So this x naught is also important. So we have an interval I, let's say, which contains this point x naught, and we wish to find a polynomial p n x of degree n. What is the condition on this polynomial? The polynomial value at x naught should be equal to the function value at x naught. Therefore, this x naught point is important, and we will discuss more little later on this, and how this is a generalization of the mean value theorem, that will also be discussed in this lecture. So now the idea is that we want to construct a polynomial of degree n which has the value at this x naught point equal to the function value at x naught point. That is the one condition. The second condition is that the first derivative of this polynomial at this x naught point is equal to the derivative of the function at that point. So the value of the polynomial, the first order derivative of the polynomial at x naught should be equal to the first derivative at x naught, and similarly the second derivative should match, and so on, and we will continue these conditions up to the nth order derivative, meaning again the nth order derivative of the polynomial should be equal to the nth order derivative of the function at that particular point x naught. So these are the conditions which we want to have for the polynomial we are constructing. So what do we expect with such a polynomial? So if, for instance, we have a polynomial where all these conditions matches, so at x naught up to this derivative order n, they matches exactly with the function derivative at x naught, and also the function value is same as so the polynomial value at x naught is same as the function value. So what do we expect? Certainly we expect that the polynomial should be close to the function f, at least in the neighborhood of that point x is equal to x naught. At x is equal to x naught, it is matching, the value is matching, but since we have many other restrictions which we have imposed in the during the construction of this polynomial, then we expect not only that the value at x naught should match, which is certainly the case as per the construction, but this polynomial should also be close to the function in the neighborhood of that point. So that we will discuss once the polynomial is ready. Now the question is that how to construct such a polynomial. It is not difficult because we have these n plus 1 condition, so definitely we can construct a polynomial of degree n having these n plus 1 restrictions on the polynomial. So this construction we consider a general n degree polynomial. So this is the n degree polynomial, as one can see here. So because x power n is there, and we have taken this special form that the constant c1 x minus x naught, c2 x minus x naught whole square, and so on. We could have also considered like c naught c1 x plus c2 x square plus and so on, and cn x power n. This is also a general form of the polynomial, but we have considered this special form of the polynomial, but both are the general n degree polynomial. So fine. So we want to determine these coefficients. So these are the unknowns of these polynomial. So we want to find out that what are these coefficients here, and we have the conditions that up to n order derivative, the value of the polynomial should be equal to the nth order derivative of the function, and the function value should be also equal to the polynomial value at this point x naught. So we have fixed one point x naught, and we have these n plus 1 conditions, and then we want to get these coefficients. We want to determine these coefficients Ci. Well, so we get the derivative. So the first order derivative of this polynomial, it is easy. So the constant, so we'll have 0 there, and then from here, from the second term, we will get 1 into c1, because the derivative of x minus x naught will be just 1, and from the second term we will get 2 times c1 and then c2 and then x minus x naught. From the third term we will get 3 into c3 x minus x naught square, and we will continue for the other terms as well. Then we will go for the second order derivative of this polynomial. So now this is the constant, so that will become 0, and from here we will get 2, and then again when the derivative of x minus x naught we take, we will get 1, and then this coefficient c2. Similarly for the other terms we can get the derivative. So we will continue this process. So the nth order derivative, if we continue, we will have only the last term. We will have only the last term, all other terms will vanish, and there also there will be no x term because it was nth order polynomial, and then we are taking this nth derivative. So we will get just the constants there. So n minus 1 and so on, 2 into 1, and then cn will be there, and this x minus x naught power 0. So this is 1. So we will not get any term of x in the nth order derivative of this polynomial. Well, now we have all these derivatives because we need here for these restrictions. And what is interesting now, and that is the idea of considering such a special form of this general nth order nth degree polynomial. So we get c naught is equal to fx naught, from where if we apply the first condition that p n x naught should be equal to fx naught. So p n x naught, so p n x naught, so all these terms will vanish at x naught, only c naught will remain, and therefore out of this first restriction we got the first coefficient, the c0, which is equal to fx naught. Similarly, when we apply this to the first derivative here, so p n first derivative at x naught, this will be equal to, so we have here the c1 which is already there, fx naught, and then plus, so in the first derivative we have here the c1, so not c naught, so we have c1 and all other terms will become 0, so we are directly getting c1. So the c1 will be f prime x naught, because p n first derivative x naught we are setting equal to the first derivative of the function at x naught. So we get the c1 as well. Similarly, when we equate this second order derivative of the polynomial at x naught equal to the second order derivative of the function at x naught, we will get this c2, which will be the double derivative of f divided by 2 into 1. and if we continue this, we can get all these coefficients up to this Cn. So Cn will be the nth order derivative of f at x naught with and divided by the factorial n. So having all these coefficients, now our polynomial is ready. So this Pnx is fx naught, then the first derivative x minus x naught, we have the second derivative divided by factorial 2 and so on. So this is the polynomial which we wish to construct, having those properties which we have set for the construction, and this is called the Taylor's polynomial of order n. This is called the Taylor's polynomial of order n. So let's go through the one example here. So what is the Taylor's polynomial of e power x? A very simple function, exponential function, and we want to have this polynomial around x is equal to 0. So always, as I said before, we have to fix a point in the domain of this function, and then we will get this expansion or the Taylor's polynomial of a certain order. So here we have taken this x is equal to 0, but we can also take x is equal to 1 or minus 1 or whatever point we need to just fix there. So for this function, all the derivatives will be e power x, and at 0 we will have e power 0, that is 1. So all the derivatives which will appear here in the Taylor's polynomial will have just value 1, and fx naught, this is also 1. So if we are talking about the first order polynomial, this is just 1, a constant value. So that means, so if this is the, so here in the graph you see this the plot of this e power x, the graph of e power x, and this is the p naught. So what do we see? That of course the value at x naught, so x naught is 0 there, should match. So that is what we see here, that they are crossing each other. So but this approximation, if we are talking about this Taylor's polynomial and we are trying to relate to this exponential function, so what do we see? That it is a very bad approximation. Other than this point, we don't see any closeness between the two. But if we go to the higher order polynomial, so let's say p1x, which is just 1 over x, so 1 will come from here and x from here. So we have 1 plus x, and if we see now, this is a first order polynomial p1x. So we do see that of course it will pass through that point itself as per the construction of the polynomial, but here now the first order derivatives also match, and as a result we have some closeness in the neighborhood of that point. So we continue this process, we go to the higher order polynomial. So p3x, this Taylor's polynomial of degree of order 3, if we compute, and then let's see how it looks like here. So this is the Taylor's polynomial of order 3, and we can see now this closeness increases. So here around this x0, it is the interval of the closeness, we see it's increasing now as the order of the polynomial is increasing. So we go to the higher and the higher order, and we see that it is getting closer and closer to the given function. So for instance, if we go up to the order 5 polynomial, then we see here that it is getting closer in a large neighborhood of this 0 point. So that is the whole idea about. So these Taylor's polynomials are used to approximate certain functions by the polynomials, because polynomials are very easy to handle. We can integrate easily, we can differentiate polynomials easily. So all these properties of the polynomial, finding roots for instance, is very easy for the polynomials. So we can use these Taylor polynomials to approximate the function, the given function, provided that we have the derivatives of the given function in hand. So now we'll be talking about that what is the relation between the Taylor's polynomial and the given function, or basically what is the error between the two. So we have a Taylor's polynomial which we are talking about as an approximation of the given function, and then we have the given function itself. So what is the error and how it is related to the order of the polynomial, because as we have seen, if we go for higher order polynomial, then the approximation to the function was good. So here we denote this Rnx is the difference between the values of the given function fx and the constructed polynomial Pnx. So this Rnx we call it remainder. So this is basically the error between the two, between the function fx and the polynomial Pnx. So we define this error term Rnx as fx, the difference between the two, fx and Pnx. Naturally this is not 0, because as we discussed that Pnx is the approximation, is an approximation of the given function fx only at the point of that expansion. So x naught, there is no error, but other than that we will have some error. So that we will analyze now, that what kind of error formula we get depending on the n. So the function Rnx is called the remainder of the Taylor's polynomial. And now the question is that how to evaluate this Rnx. So we will evaluate this by considering that Rn at x naught, or the derivative R of Rn at x naught up to nth order derivative of Rn at x naught, all these are 0. Why? Because we know already that Rn x naught is just the fx naught and minus this Pnx naught, and as per the construction these two values should match, should be the same. So it is equal to 0. Similarly for Rn x naught will be the derivative at x naught and then minus this Pn, the derivative at x naught, and as per the construction also these should match, and this will continue up to the nth order derivative, because our construction was that all these derivative up to the nth order, they should match for the polynomial and the function. So this will be also 0. So we have this observation that the Rn at x naught, in fact all these derivatives, the first order, second order up to nth order, they will be 0. Well, so having this, we also consider one more function gx, which is x minus x naught, which is x minus x naught power n for all x in I. So I is the interval which contain this point x naught. So we consider a function x minus x naught, this is a polynomial and n plus 1th degree polynomial. So this is given now, the gx, and here also if you observe closely what is the property of gx, that here also at x naught the function value is 0, the first order derivative, second order derivative, in fact up to the nth order derivative it will vanish, because there will be always a term x minus x naught in all these derivatives, and n plus 1th derivative will be just the factorial n plus 1. So and all other will be 0, all other derivatives will be 0. So considering this function and these properties, let's consider x any point in the interval I, and suppose this is just for the sake of convenience, so we take either x is bigger than x naught or x is smaller than x naught. So let's consider this, that x point which we have picked is bigger than x naught. And now we apply the Cauchy mean value theorem. So here also we have a nice application of the Cauchy mean value theorem to find out this error or the remainder term. So we use Cauchy mean value theorem for Rn. There is a function Rn which we have defined, and this g in the interval x naught to x. So the Cauchy mean value theorem was Rnx minus Rnx0 over gx minus gx naught must be equal to Rn, the first derivative, divided by first derivative of g at some point xi I, and xi I lies between x naught and x. Well, so here we have already seen that this Rn x naught is 0 and also gx naught is 0. So what do we get here? Rnx over gx is equal to the first derivative here, the first derivative Rn prime divided by g prime at xi 1. So we apply the Cauchy mean value theorem now on Rn prime and G prime. So now we are considering the function Rn prime and G prime. This result we have already when we have applied this mean value theorem before on the function Rn and G. Now we are applying the Cauchy mean value theorem on the derivative. So Rn derivative, this is one function, this is also another function. We are applying the Cauchy mean value theorem now on these two functions. So as a result, what we will see, Rn xi1 minus n in the interval x naught xi1. So Rn prime xi1, Rn prime x0, G prime at x naught, and the double derivative terms will come because the derivative of these derivatives. So we have the derivatives there in the right hand side. This result we already have before, and we also know that Rn derivative is 0 and G derivative is also 0, that we have already seen before. That is the property of Rn and G. So what do we get here? We get in terms of the derivative at xi1, but the derivative of this xi1, this ratio is nothing but the Rn and G. So finally we get this Rn divided by G is equal to the second derivative. We can continue this construction, and what we will realize at the end, that Rn x over G x is equal to the n plus 1th order derivative at xi n and n plus 1th order derivative at xi n plus 1, where xi n plus 1 exactly will move towards x naught here. So again here, like interval we have considered x naught to xi 1, then we will consider in the next stage here our interval x naught to xi 2 and so on, and then finally we will achieve continuing this Cauchy mean value theorem, we will achieve that this Rn x, this ratio over Gx is equal to this one here. So just recall that Gx was x minus x naught power n plus 1 and its derivative is just factorial n plus 1. So we can replace here by the factorial n plus 1. So what do we get? We get Rn x is equal to the n plus 1th derivative divided by this factorial n plus 1, and this Gx which goes to the right hand side, here we have x minus x naught power n plus 1, and this xi which we have replaced for this xi n plus 1 is somewhere between x naught and xn, because all these xi's here were between x naught and xn. So here we have, just for simplicity, instead of saying xi n plus 1, we use the xi, and the restriction is that the xi is somewhere in between x naught and x. Well, so we have this formula for the Rnx. We will further simplify it because we don't want to write in terms of Rn itself or the derivative, but this we can easily get in terms of f. So Rnx was fx minus pnx, and if we go for the n plus 1th derivative of this, then we will get fn plus 1 minus pn n plus 1, and this pn n plus 1 will be 0 because this was the n order polynomial, and the n plus 1th order derivative will make it 0. So what we have only the n plus 1th derivative of this x. So this Rn, the nth order derivative, n plus 1th order derivative is equal to the n plus 1th derivative of f. So this Rnx, we replace this n plus 1th order derivative by the function itself. So we get this one, x minus x naught power n plus 1, and this is called the Lagrange form of remainder. So we have this error term which contains the n plus 1th order derivative at some xi, which xi lies between the x naught and the point x, where we are estimating this, or we are computing the error. You have n plus 1th factorial and x minus x naught power n plus 1. So that is the formula, that is the error formula, or that is the remainder formula, and it is called Lagrange form of remainder. So there is another form for the same formula here, that instead of writing this xi, because we know that the xi lies between x naught and x, so that can be also written in this form. So x naught plus some theta here and x minus x naught. So if theta is approaching to 0, for instance, this argument will approach to x naught, and theta approaching to 1, then in that case it will approach to x. So this argument is same as xi here, this is same as xi. Xi was also between x naught and x, and this expression for different values of theta will be also between x naught and x, and the rest everything remains the same. So this is either this one or this one. These forms are called Lagrange form of remainder. There are various other forms in the literature, and we are not going to derive this in this lecture. So this is the Lagrange form which we have already seen. There is a Cauchy form, so there is a slight difference one can clearly observe here in this numerator as well. And there are many other different forms. In fact, we have the integral form also for the same remainder, and we have another very different form of the integral. So there are various forms, but the most popular one is the Lagrange form of remainder, which we have already derived. So Taylor's theorem or Taylor's formula. Now to conclude here, so we have fx is equal to fx naught. This is what we have derived. So the first derivative x minus x naught square, and so on, and this is the remainder term. So the remainder as well, we have seen that it will have n plus 1th order derivative at some point xi, and then this xi will be from x naught to x somewhere. As a special case, if we look at the special case for n is equal to 0, so this was for n. So if we say what will happen to n is equal to 0, so we will have fx0, and then we will have a remainder term. So fx is equal to fx0, and then the remainder term here f prime xi over factorial 1 x minus x naught. So see, this fx is equal to this. Here we have the equality because we have kept this error term also, the remainder term there. Therefore we are writing that equality. If we talk about the Taylor's polynomial here, this is some kind of approximation to fx, but writing with the error term, we have the equality to fx. So here, getting back to the special case n is equal to 0, what we realize now that this is nothing but the Lagrange mean value theorem, which we have already studied. So as a special case, when n is 0, this Taylor's formula reduces to the Lagrange mean value theorem. So one remark, so if we set x not equal to 0 in this Taylor's formula of this function fx, this is called Maclaurin's formula. So there is no other difference, only for x not equal to 0 it is called Maclaurin's formula, which we have just discussed. And in the Taylor's formula, if this remainder term goes to 0 as n goes to infinity, in that case that Taylor's formula can be written as a series, and this is called Taylor series, and for x is equal to 0 this is called Maclaurin series. To write that Taylor's formula into a Taylor series, we need to show actually this condition whether Rn x goes to 0 as n goes to infinity or not. Once we have this condition, we can write down fx is equal to in the form of a series. There are many examples of smooth functions, so the things are little complicated, because if we write the Taylor series, we are talking about the series because there is a question whether that series converges or not. So there are several examples in fact of smooth functions whose Taylor series diverges everywhere other than the point of expansion, because the point of expansion anyway you will have equality always. There are examples of the smooth function whose Taylor series converges to some other function. So it may happen that the series which we are writing, it may converge to some other function. Therefore the condition which we have mentioned before, that Rn x must go to 0 as n goes to infinity, then only that fx is equal to that Taylor series. A very simple example, if we consider this fx is equal to this one can easily show that all n order derivative, first order, second order, all are 0, and so we can write down the Maclaurin series because all derivatives are 0, 0 plus 0 plus 0, so everything is 0 there. So this series converges, and it converges to 0, but it does not converge to the given function. So a very simple example we have seen that for this function, the Maclaurin series, if we write down, that does not converge to the function value. It converges in this case, but it does not converge to the function value fx. This is identically 0 for any value of x. So that is the here we have to be bit careful. just one or two examples here. So the Maclaurin series of e power x, if we want to write, we know all the derivatives of exponential function are just 1. So we can quickly write down that e power x is 1 plus x square and so on, and we have the remainder term. The remainder term also, from the formula we realize this one, and since we know the n plus 1th derivative, so it will be just e power theta x. So this is the remainder term here, and now we will show here that this remainder term goes to 0 as n goes to infinity for this case, and then we can write down this exponential function in the form of a series. So this Rnx with this remainder formula, we will show that it goes to 0. So we write down the absolute value of Rnx as absolute value of x and factorial n plus 1 e power theta x, as it is a positive quantity, so we did not put any absolute value here, and this is finite for a given x. So whatever x we have, this is going to be a finite number e power theta x, so we are not much worried about this number. So for a fixed x, so x can be anything, but for a fixed x, so we are not taking a particular x, it can be any x, but whatever we take, however large or small, it is a fixed number, and we can always find a natural number n such that this n is even bigger than the absolute value of x. So this is possible, and then we choose a small n which is even bigger than this number n, which was bigger than the absolute value of x. So having this small n, now we will write down this quotient here, mod x power n plus 1 over n plus 1 as a product. So here the factorial n plus 1 is 1, 2 and so on n plus 1, and in numerator we have the absolute value of x power n plus 1, and then we break into the product. So we have the absolute value of x divided by 1, then absolute value divided by 2. So we have n plus 1 terms there, and here also in the denominator we have n plus 1 terms. So we have written in this form, and as we can realize, because we have chosen this n bigger than, because at the end we will be observing that what happens to Rn when n approaches to infinity. So we can choose this large small n which is greater than big N, therefore this big N term is coming in between, and then we have this n plus 1 term at the end. Well, so if you observe these terms here, mod x over n, so here mod x over n is less than 1. So we set this to q now, which q is less than 1, and these terms, the following term of this will be even less than q. So what we can replace all these by q's and set everything to less than. So here this term is less than, so here all these have been replaced by q, and therefore this symbol less than has come here in the inequality. So this is q into q, and then that is q power. So we know that how many terms are there, because here we start with n and ends with n plus 1. So we are here with so many terms, and that is the q power n minus n plus 2. And now at this stage we can actually take the limit. So if n goes to infinity, because this is something fixed here, and if n goes to infinity and q is less than 1, then this term will go to 0 and everything will become 0. So here we have seen that this absolute value of this Rnx is getting to 0 as n approaches to infinity, and therefore we conclude in this particular case that the remainder term will go to 0, and therefore we can write down e power x in the Maclaurin's form, as a Maclaurin series, because Rnx goes to 0, then e power x must be equal to this series here. Well, this is the last example. So for what values of a, the coefficient of x power 100 in the Maclaurin expansion of this is this. So the coefficient is given, so we can find out the Maclaurin expansion easily and then equate to this coefficient, and then we can find out what is the a here. So fx is given, this one we can get the derivative, and in fact the derivative at 0 is also easy to compute. So we can get the nth order derivative also, only thing is this na will come in the nth order derivative. The second order derivative, this 2a extra term will be coming, and at the value of this nth order derivative at 0 will be 3 plus Na. Now we can write down the Maclaurin's expansion, and it is given that the coefficient of x power 100. So we know the coefficient of x power 100 will be 1 over factorial 100 and 100th derivative at 0, which we can easily find out from here. So comparing this, so f 100 at 0 factorial 100, it is given at 83 by 100. This is nothing but 3 plus 100a, and then this factorial will cancel out and we will get a is equal to 4 by 5. So we can do similar kind of problems where the coefficient values is given and then some unknown parameter was there in the function, which we have found out that this is actually 4 by 5. Well, just to conclude, so we have gone through this Taylor's formula. So this was the Taylor's formula with Rn, yeah. So fx is equal to this Taylor's polynomial and plus the remainder term. This is called the Taylor's formula, whereas these terms are called Taylor's polynomial, and the remainder was given at least one form, which was the Lagrange form of remainder. And we have also observed that if Rnx goes to 0 as n goes to infinity, then this Taylor's formula can be written as in the form of a series, which is called Taylor series. Well, so here we have some references which are used to prepare this lecture, and with this I thank you very much for your attention.